Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Welcome friends to the lecture on environmental loads sequel. In this lecture, we are going to talk about wind loads. This is a part of the SwayamPrabha course titled Maritime Structures offered by Department of Maritime Engineering at IIT Gandhinagar. In this lecture, welcome to understand more about the wind loads acting on maritime structures, which is one of the major component or constituent of environmental loads acting on maritime structures. Friends, wind loads are generally caused by complex fluid dynamics phenomena. It is rather very difficult to calculate or assess the wind loads accurately on structures. It is not that there is no mathematics available to do this, but they are very randomized phenomena. There are many parameters which affects their composition and assessment on structures. Therefore, accurately it cannot be computed, but there are closed form solutions available, equations available, which help us to compute them, and most of these equations depend on empirical parameters where there are certain assumptions which make them valid only within certain range of variables, which we will see them in detail. Most widely, engineering approach is used to compute wind loads. But of course, there are certain set of assumptions which we need to understand. Let us see what are those assumptions we make. These assumptions are also limitations which prevent you from assessing wind loads accurately. Okay? One, when a stream of air flows with constant velocity v, it will generate a force on a plate or a surface which is kept perpendicular to the direction of flow. For example, if I have a plate of certain thickness and if I allow the wind to flow in this direction and the wind is flowing with a constant velocity v, it will exert a force on the surface and this force will be perpendicular to the surface, okay, 90 degrees to the surface. You may ask me a question, what is the guarantee that wind will always exercise force only on the surface, normal to its application of flow? Yes, that is a good question. If I have a wind flowing in any specific direction to this, I will get the components of this and compute them. Okay? For example, if this is my f dash, I can say this is f dash cos theta and this is f dash sin theta. So, I can always resolve this in two components, one normal to the plate, one tangential or parallel to the plate. Okay. So, therefore, we assume that when a stream of air flows with a constant velocity v, it exerts a pressure or a force on a plate or a membrane or a member which is kept normal. Therefore, in terms I can say obstruction to flow causes force. Okay? When you are obstructing this flow by a plate, by keeping a plate in the field of flow, it causes a force or a pressure, right? So, obstruction to flow causes force. The second one, this force is proportional to the velocity. In fact, in wind we call them as speed. Okay? Same meter per second, velocity or speed, we call them as speed. So, I can say this wind force is proportional to velocity. I'll then equate it to a value using some proportionality constant, which I will discuss. And this proportionality constant can be computed like what you are saying here. Therefore, I can now say wind force acting on a plate placed orthogonal, I say, okay, normal 90° orthogonal to the wind direction is given by Pw is proportional to V square. We said that. Now, I say it is equal to half rho A Cw of V square. So, I can call this as the constant of proportionality, equation number 1. Whereas, in equation 1, rho A is the mass density of air, which is approximately 1.25 kg per cubic meter. Cw is wind pressure coefficient. So, now I would say, if I place a plate of certain thickness in a direction normal to the wind, it exerts pressure. Okay. Now, this wind velocity has got a trend of varying not only with space, but also with height. So, the wind velocity has a trend to vary with height. I think that we all know, when you stand on a tall building 30, 40 story high, you will find the wind pressure much more as compared to you stand on a single or 2-story building. So, as you go higher and higher, as you fly in the aircraft, and you will notice that there are a lot of suction pressure acting, what they call in aviation language as turbulence. So, as you go higher and higher altitudes, you will notice that wind pressure is significantly high. So, wind has a tendency, or wind velocity has a trend to increase with height. Similarly, in every geographical location, the wind velocity in direction keeps on changing. Therefore, I can say wind essentially is a dynamic phenomena. Now, it is important to note that the mass density of air, what we call as rho A, increases near the splash zone. This is due to the water spray near the MSL. Suppose if I have this as the seabed, this as a mean sea level, I have an offshore element, offshore structure, structural member, let us say which is fixed to the seabed. I want to compute the wind pressure at this point P. Okay, we have just seen it is Pw. Now, in this segment, the mass density of air is higher because of the concentration of water jet spray available in this segment. Okay. So, that is what I say. Near the splash zone, this zone is called splash zone, we already know that. Okay. This is called splash zone. Okay. And this is called atmospheric zone. And of course, this is called submerged zone. Okay. So, in the splash zone, the mass density of air is higher, and how does it bother us? Because mass density is a multiplier here, right? It is a multiplier. So, therefore, wind velocity though may be equal and lesser at that level, the pressure caused by wind is more because the mass density is higher near the splash zone. Okay. Having said this, we also assume that it remains constant up to 20 to 30 meter above mean sea level. Now, I do not want to stop at the pressure, I want to find the force. So, the force caused by wind is pressure caused by wind multiplied by the area. Suppose I have a plate of certain thickness, I want to find the pressure at this area. I know the breadth, I know the depth of this hatched portion. So, area now becomes B into D and pressure is acting normal to this. I can always find the force is that pressure multiplied by B into D. If you want to find alternatively the wind force for the entire area, I can always find the breadth of the entire area, height of entire area, compute that here. Okay, it is very simple. So, wherever I want, I can compute pressure. If I know the pressure, I can find the force. So, I am now converting pressure exerted by wind on any surface normal to it to a force equivalent to that using this equation. Agreed? So, equation 2. Similarly, if the plate is not kept normal to the direction of flow, but at an angle, I can always resolve that normal and parallel to the plate and find out the components of that force. Now, coming to the other component of what we have in wind force, the Cw, which is the wind pressure coefficient. The wind pressure coefficient Cw depends on the Reynolds number of the flow usually it is 0.7 to 1.2 for cylindrical members. So, one can get an idea about this coefficient. Furthermore, friends, when the wind naturally blows in atmosphere, wind has got two components. The first component is what we call as the mean wind component, which is a static component which does not vary with time. The second component is the fluctuating component, which is called as the gust component, which is dynamic in nature. Let us express this graphically. I have a wind phenomena like this. This is time, this is velocity. I can now split this into two parts. One, a mean component, okay, only this part. What I do? I have a mean component. Then I pick up these variations, friends carefully see here. I pick up this variation, this variation, this variation, so on, and mark them here. So, this component is called the mean wind velocity, which is called as V bar. This component is called the gust wind component, which is called as V of t. I can now say velocity of wind has got two components, V bar plus V of t. I can say this as capital V of t as this, equation 3. So, wind has now got two components, the gust wind component and the mean wind component. So, it is interesting friends, the gust component is very less compared to the mean component. So, if V of t is a sum of V bar plus V of t, I can say this is not simply is V bar, okay, V bar plus V of t. I can now say V bar with the mean wind component is much higher than the gust component. Okay, is much higher. So, generally people ignore the gust component and treat wind as a quasi static phenomenon. But to compromise on this loss, people use something called gust factor. We will see what it is. Now, we understand that wind, wind has got two components, V bar plus V of t. Wind force, which is actually pressure multiplied by the projected area, pressure half rho C W V bar V square and multiply by area has got now two components. One, the drag component, the drag force, which is half rho C D V square area, and the second component is the lift component, which is half rho CL V square into area. Let us also keep this as capital, right, for our understanding, V square into area, where this V is exactly this. Okay. So, there are two forces now. Let me put the equations as 4A and 4B. Okay. Now, CD is called as the drag coefficient, CL is called as the lift coefficient, A is the area measured perpendicular to the wind velocity, and of course, rho W we already know. So, now I can say FD, the drag component, the drag wind force acts parallel to the wind direction. It is called drag. It drags the structure. The lift component, the lift force, okay, acts perpendicular to the wind direction. Suppose if you have a body in plan, the wind is blowing this direction, the force acting parallel to the direction on the body are called drag forces. Okay. the force which is acting perpendicular to this. There are two perpendiculars, one is in plan, other is in elevation. This is also perpendicular, no? So, lift force. Okay. So, respective coefficients need to be added for these perpendicular components and parallel components. Since wind is a random phenomena, the wind velocity is given by a power law. This power law says Vz is V10 Z by 10 to the power 1 by 7, equation number 5, where Vz is the velocity of wind at any height Z meters from the ground. If it is maritime structures, we say it is measured from the mean sea level. Okay. V10 is the mean wind velocity at 10-meter height from the datum. Okay. Measured above the datum. Okay. Measured above the datum. Above the datum. Z is any height in meters measured above the datum. We say the datum is MSLE. Okay, you will notice that in this equation, up to 10-meter height, okay, the wind velocity remains constant. After that, it varies exponentially. So, I can plot if I have a cylinder or circular member, and if this is my mean sea level, if this is my z equals 10 meter, the datum height, I can say the wind velocity varies no variation. After this, it varies. Okay. So, this is given by that 1/7 power law, which we saw the equation. So, this 10 meter is called the reference height, up to which wind velocity remains constant. Okay. Friends, as I said, wind has got two components, the mean component and the gust component. This is called the mean component, mean wind, and this is called as the gust wind. Now, the gust component is very less compared to the mean wind. So, people generally consider in analysis purposes wind as a quasi-static model where the gust component need to be compromised by some factor. We call that as a gust factor. So, the average gust factor, which can be used, which I call as Fg, which can be used to compromise the effect of neglecting gust on the wind velocity, is taken approximately as 1.35 to 1.45. It means you enhance the mean wind velocity by about 35 to 45% to account for the variation caused because of dynamic effect of wind. Okay. Now, the question is, what value would you take for the mean wind? Now, for maritime structures, the mean wind component is taken as the sustained wind speed, which is used for the design. essentially this is actually 1 minute wind speed record of average wind speed. So, what you should do, you should measure the wind speed on any offshore location for a minimum duration of 60 seconds, take an average of that, that is what we call a sustained wind speed, and that should be used. Now, the question is, at what time in a day, at what season in a year, at what direction in geography will you measure this? Is it not? That is a very important situation. So, you have to do this for a specific period over which an average need to be worked out. So, this is advised by US Weather Bureau, and they say use the FG component based on the sustained wind speed taken at the same offshore location at different seasons in a year at different time on a day. Okay? Use that as 1 minute average record, and that is what we say as V bar. So, V of t is this V bar plus small v of t. I can neglect small v of t by using a gust factor, but I have to use this based on this record. In maritime design, we also use something called fastest mile velocity. What is it? Fastest mile velocity actually is equal to the sustained wind speed multiplied by gust factor. Okay? We use this for the design. And one may ask me a question, how long I should take this average? As we say, take an offshore location, different season in a year, at different time on a day, how long I should take this? Okay, that is very interesting. The return period of this data is actually referring to 100-year sustained wind speed. So, you have to look at 100-year record of sustained wind speed, then take that as an average for V bar. Now, in the absence of such data, one can use sustained wind speed as 125 miles per hour. Okay, 125 miles per hour. If you have the record, you can use them, otherwise this can be used. Friends, the equation what we saw, which is giving me Vz as V10 to the power z by 10 of 1 by 7 is based on empirical law. Okay. It is very commonly used in maritime design, and it has got a very good agreement with the experimental observations. Okay. Let us put some important points together for wind velocity. There are some factors when you compare wind and earthquake. Let us do that also for understanding. Earthquakes and wind are usually orthogonal to each other. It is a natural phenomenon. Okay? I mean, there is no guideline for this, why they are orthogonal to each other. In the direction of application, they are generally normal to each other when they act on maritime structures. Therefore, friends, wind induced vibration is very important and is very dominant in flexible structures, whereas earthquake forces are dominant in fixed structures. We already know by this time what are the classification of fixed and floating structures and flexible structures. We can easily identify now on what structures which kind of forces are dominant. When you compare wind and wave, that is interesting. Wind and waves in simple terms are considered to be friendly, very friendly. They act together. Okay, whereas earthquake and wind are opposite, 90 degree to each other, right. There are few points which we must remember before considering wind as a force in maritime structure. One, V of t is V bar plus small v of t. 2, wind produces low frequency excitation. 3, the fluctuating component of wind. Can you tell me what is the name of this component? Yes, you are right. This is called gust component. Fluctuating component of wind is modeled based on probabilistics theories. 4, the drag force on members will be due to wind and wave, but wave alone creates inertia effect on the members and earthquake forces create only the inertia effect on members. No drag force, okay. Earthquake does not create drag force, whereas wind and wave creates drag force. The next point, vibrations induced by wind and wave are different from those induced by earthquakes. Okay. Next, for design, most of the codes of practice treat wind as quasi static process. The dynamic component of wind is generally neglected in design, and that is accounted for by taking into account the gust factor. So, wind induced response is very important in slender and flexible structures. Okay, is very important idea. So, when you are designing a flexible or a slender structure, wind induced response is very dominant. So, one has to be very careful about analyzing these forces. Now, considering wind as a dynamic phenomena, following points are important. Let us see what are they. 1. Length of the record. How much record do you take for computing the wind speed? The record what you consider for computing mean wind speed should be a continuous record. You cannot take an intermittent record to compute the mean wind speed. This should be based on the period and service life of the structure. The second issue is the average time. You have taken average, no? How much the average time you should take? Average time is the time at which the record is averaged. Okay? Wind spectrum helps us to present these variations in a statistical manner So, let us see what are different wind spectra available in the literature. Wind spectra are expressed in terms of circular frequency. You know friends, omega is the frequency which is in radians per second. F is also called as a frequency because cyclic frequency which is expressed as number of cycles per second. T is the period. So, omega is 2 pi by T and T and F are inversely proportional. Okay, I can now also say omega is 2 pi F. Okay. So, the commonly used spectrum for wind spectra for maritime structures. Say wind spectra are as follows. 1. We have something called Davenport spectrum. Equation is omega S u plus omega. There is one sided power spectral density function del u bar 10 square is 4 theta square by 1 plus theta square of raised to the power 4 by 3. Equation 6. Omega Su plus by del U10 4 theta square by this. The second spectrum which is used is called the Harris spectrum. Harris spectrum considers the spatial variation effect of the gust and the mean wind speed. This spectrum is not recommended for frequency lesser than 0.1 hertz. Okay? So, the equation is omega s u omega by del u bar 10 square is given by 4 theta by 2 plus theta square of 5 by 6. You will find there are differences between the spectra given by each equation. Okay? They are all empirical equations based on experimental observations. In both these equations, theta is called derivable variable and theta is given as omega Lu by 2 pi of u bar 10 omega by 2 pi I can always say it is frequency Lu by u bar 10 and this is valid for all range of omega up to infinity. In this case Lu is called integral length, usually taken as 1200 for Davenport spectrum and taken as 1800 for Harris spectrum. So, it is a constant. Okay. L is called the surface drag coefficient. Usually this value is taken as 0.001. Friends, both these spectra are not useful directly for maritime structures because they are both these spectra are actually derived for land based structures, not for maritime structures, but it is commonly used in maritime structures design also, but it is not. So, then for maritime structures people use something called chimal spectrum, which is given by Dribby and Hazen 1997. According to the spectrum, omega SU omega by sigma u square is given as 6.8 theta by 1 plus 10.2 theta to the power 5 by 3, where theta in this case is expressed as the ratio of omega to omega p, and where omega p is called the peak frequency and sigma u square is a variance of u of t at 10 meter. That is the reference height. Okay? Variance of this, not square of this, variance of this. The next spectrum used is an American Petroleum Institute spectrum given in the year 2000, specifically recommended for maritime structures. Omega SU omega by sigma u square is omega by omega p 1 plus 1.5 omega by omega p to the power 5 by 3. So, now it has got a range of application 0.01 less than or equal to omega p into z by u bar z less than 0.1, this equation is valid. So, for design purposes usually a value of 0.025 is chosen for design purposes. Okay? It is between this and this, but we choose this for design. Now, sigma uz is given as 0.15 of u bar z Zs by Z 0.125 if Z is less than Zs. Otherwise, 0.15 u bar Z Zs by Z to the power 0.275 for Z greater than Zs, where Zs is called the thickness of surface layer, usually taken as 20 meters. So, friends, I have got different spectra available in the literature which helps me to compute the energy concentration of wind. If we typically try to plot them, they all look like this. I plot them with theta as the variable and S omega SU omega this power spectral ordinate as this. So, I can draw them, let us say, let the put as values as 10 power minus 2, 10 power minus 1, 10 power 0, that is 1, then 10 power 1. Let us plot this. Okay. I am just drawing a vertical line for our understanding to make a grid. Similarly, 10 power minus 1, then 1, then 10, then 10 square, okay, then 10 cube. Let us say a grid like this. Let us try to plot the first spectrum, which is Davenport, starting from 1, it touches somewhere here and goes to 10 and drops down here. This is Davenport. Of course, equations are there, you can try to plot them. I am giving a simple illustration. API starts from here and just parallelly touches here. This is API spectrum. Aris starts from in between, touches this point and then goes down. Friends, you will notice that in all these three spectra, at low frequency, okay, energy is higher, is it not? At higher frequency, energy is lower. So, we say wind therefore is a low frequency phenomenon, okay. And you will always see at larger frequency, the variation between them is very minimum. At low frequencies, the variation between them is significant. So, one should choose the appropriate spectrum for design correctly if to compute the wind forces correctly in offshore structures or maritime structures. So, friends, let us come to the summary. In this lecture, we learnt about another environmental load, which is the wind load. Wind load induces pressure and that pressure causes force which is perpendicular to the flow direction. It has got two components, the drag component and the lift component, which either drags the member along the direction of wind or lifts the member normal to the direction of wind. We have to use appropriate coefficients to compute. Wind, of course, velocity has two components, the mean component and the gust component. The gust component is very less in intensity compared to the mean component. Therefore, wind is always handled as a quasi-static process. If I know the wind velocity, I can always find the force, which is half rho w Cw V T square multiplied by the area, where area is normal to the direction of wind, and so on. So, we can also use 1/7 power law to compute this variation of wind along the height. Alternatively, I can also use spectra recommended by various codes of practice for using in design of maritime structures. So, Friends, this lecture is just a curtain raiser of understanding environmental loads, wind as one of the segment of an important load applied to maritime structures. In the last two lectures, we saw about the wave forces. Then subsequently, we will discuss about earthquake forces and ice forces, which are special forces acting on maritime structures. We already saw the fire load or explosion and blast loads coming on maritime structures. So, they all comprise to various kinds of forces that act on maritime structures. Thank you very much. Namaste.